this is Dr. Rahul Haware from the channel Ask Applying Scientific Knowledge. I welcome you in this fourth video of Rheology, where we are going to talk about what are the Newtonian liquids. But before that, if you have missed our previous 3 videos, I'm giving you the link of those videos in the description box below. So please do check those videos to get a continuity of this topic. So as you can see here, we do have a portrait of a famous English mathematician from 16th century, and his name is Sir Isaac Newton. And Sir Isaac Newton was the first person who found out that there is a certain relationship between shearing stress and shearing rate. And the liquids which follow that relationship are called as Newtonian liquids. So let's dig more into about Newtonian liquids in next couple of slides. As I said, there is a certain relationship between shearing stress and shearing rate. And what is that certain relationship? Of course, there is a proportional relationship between shearing stress and shearing rate. So what Sir Isaac Newton found, when he increased the shearing stress, he found out that there is an increase in shearing rate. And liquid which follow that proportional relationship are called as Newtonian liquids. Liquids which follow that relationship are called as Newtonian liquids. As we have seen in the previous video, we know that shearing stress is force per unit area, and it is denoted with letter tau. And this is the shearing rate, which is denoted with letter gamma dot, and is equal to delta U, which is a change in velocity, and delta Y is change in separation between the plates, isn't it? You want to do some changes in the liquid plate separation in order to flow. It's not only that, but it depends on a lot of factors. As I said in my previous video, it depends on the velocity, and it also depends on the time. So when tau is proportional to gamma mu, and when liquids follow that relationship are called as Newtonian liquids. So we know that tau is proportional to delta U over delta Y, and I would like to get rid of this proportional sign. And how I can do that? Well, I can induce equal sign, and then I have to replace it not only with equal sign, and I have to induce some constant. So I can say C, but I don't have to include C because they're already international community have decided what will be the name of this constant, and they call it as eta. That's a Greek letter eta. Okay, so we don't have any other chance to include our constant there. So eta is equal to coefficient of viscosity, and as I said, Sir Isaac Newton found that when there is an increase in shearing stress, there is an increase in shearing rate. But please keep in mind, it starts from the zero, from the origin. So at 0, when there is no shearing stress, there is no shearing rate. These liquids follow this relationship. So if you increase the shearing stress, let's say 5 dynes per centimeter, you will get, let's say, 5 centimeter inverse. Sorry, not centimeter, 5 second inverse shearing rate. If you apply 10, it might get 10, who knows. 10 dyne per centimeter square shearing stress, you will get 10 second inverse shearing rate. If you apply, let's say, 20 shearing stress, 20 dynes per centimeter square shearing stress, you will get 20 second inverse shearing rate. And that's why it is called as proportional relationship, isn't it? It might be like when you are applying 5, it will be like, let's say, 20, it will like in that it will be 40, and it will be 80, like that. Okay, these numbers will get varied. Important thing here is that you can take a slope of this. Let me rub it out, this one. And by the way, these liquids are called as Newtonian liquids. And from the slope, let me rub it out. As I said, you get the viscosity directly. Okay, from the slope you get viscosity directly, and you can take slope in any region. From here also, that slope will not change. If you take slope from here to here, that number will not change, and that has an implication, and I will talk more about that one in next couple of slides. So let's dig more into the Newtonian systems. As we know that force divided by area is shearing stress, and delta U or delta Y is shearing rate. And Sir Isaac Newton found out that proportional relationship between shearing stress and shearing rate. And we want to get rid of this proportional sign. What we did? Well, we introduced equal sign, and then as we don't have choice for another coefficient, we have to go with international conventions. So we have to add that coefficient, and that is eta. And what is that eta? Eta is dynamic viscosity. So now let's figure it out, the units of shearing rate and shearing stress. So what is the shearing rate? Delta U over delta Y. And what is delta U? Well, it is the velocity. It is the velocity, and velocity is distance over time. How you are measuring the distance? Well, it's in centimeter. And how you are measuring the time? Well, it's in second. Now, how about delta Y? Well, delta Y is separation between the plates. So again it is a distance, isn't it? Again it is a distance. So how you are measuring the distance? Well, again in centimeter. So this centimeter and this centimeter get cancelled. So the unit of shearing rate or shear rate is second inverse. Now how about shearing stress? Well, it is a pressure, isn't it? Force per unit area. So dyne divided by centimeter square. Dyne is equal to gram times centimeter divided by second square. We are just plugging those things. 1 centimeter will be going away. So the final shearing stress unit will be gram divided by centimeter times second square. So let's plug this one and this one in our viscosity units or viscosity formula. So shearing stress divided by shearing rate, gram divided by centimeter times second square divided by 1 over second. So that second and 1 second will be gone, and we will come up with this final units. Gram times centimeter inverse times second inverse. So this is really full form. So we want some abbreviation, isn't it? And what we call, we come up with this abbreviation called as poise. We want to poise this one. I'm just joking. So let me rub it out, this guy here. So in industrial pharmacy, the viscosity is expressed as centipoise. Viscosity is expressed as centipoise. And 1 centipoise is equal to 0.01 poise. Now, if you remember, previously I was talking, Sir Isaac Newton, he found out that when he increased shearing stress, he found shearing rate is increased. So shearing stress is an independent variable, so it should be on the x-axis, and shearing rate is on y-axis. That's the observation. That's the observation, isn't it? And that's the dependent variable. That's the dependent variable. And if you take the slope of this, now 1 divided by slope will be fluidity. So as I said, what Sir Isaac Newton did, he increased the shearing stress and then he observed the shearing rate. So shearing stress is, I'll write in full words. By the way, my handwriting is not that great, just like Word. Shearing stress is dependent variable. And what is the shearing rate? Shearing rate is independent variable. That's what you have observed. And when you take the slope, that will be the fluidity, isn't it? So this is a y variable and this is a x variable. So this is a independent variable and this is a dependent variable. Why I am calling it as a dependent variable? Because shearing rate is depend on shearing stress. When Sir Isaac Newton, what he found? Well, at zero nothing is happening. But when he increased the shearing stress, he found that shearing rate is increased. So let's say again, I assume, let's take an example. If we increase the 5 dynes per centimeter square shearing stress, he might have found, I don't know what he found, but let's say for one liquid we have 5 second inverse shearing rate. When I'm increasing the shearing stress by double, like 10 dynes per centimeter square, the shearing rate might be double. That's the proportional relationship. If I'm increasing the shearing rate by triple as compared to this one, 5 times 3 is equal to 15 dynes per centimeter square, the shearing stress should be triple, isn't it? So it should be 15 seconds square. And from the slope you get the fluidity. Let me rub it out. From the slope you get the fluidity. And one more thing is, I'm trying to tell again, if you take the straight line equation, it is y is equal to mx plus c, but c is 0, so no y-intercept in Newtonian liquids. Again, I'm talking or stressing on that one because that has another implication, and you will see in next few videos. Okay, so Newtonian liquid relationship starts from the beginning, from 0, and in this case from the slope you are getting 1 divided by eta, and that is the fluidity. And if you want to calculate the viscosity, it is 1 divided by slope for this plot, okay, where shearing stress is on x-axis and shearing rate. But as we know that in case of pharmacy we are a little bit lazy, okay, and that's why we decided to switch the things, because we are always interested in viscosity, not in fluidity. And that's why what we decided, well, we'll put shearing stress on y-axis and shearing rate on x-axis, okay, and then from the slope you directly get the viscosity. So you are easing your life, and that's what you want to do. But technically or mathematically, this is the correct approach. This is the correct approach, okay. You should have always independent variable on x-axis and dependent variable on y-axis, and that's why you will see the old pharmacy text and research articles, they always follow this one, not this one, okay. So let's talk more about the plot of Newtonian liquids. So it's now clear, when you have shearing stress on y-axis and shearing rate on x-axis, we are directly getting viscosity, and the 1 divided by eta is equal to fluidity. Now let's think about the liquid A and liquid B. What is the unique thing about liquid A? If I take a slope from this region or this region, it doesn't change. Likewise with liquid B. If I'm going on this line, which is traveling from 0 again, or starting from 0, when I'm taking slope of any region, it's not changing. What does that mean? That slope will not change. Slope is not changing. As you can see here, the slope of the shear stress versus shear rate is constant. So as the slope is not changing, the viscosity of Newtonian liquid is not changing, and that's why it is called as absolute viscosity. That's why it is called as absolute viscosity. That is the unique property of Newtonian liquids. Their viscosity is not changing. Their viscosity is absolute. So here I would like to stop my video, and I hope you have enjoyed this video. If you have enjoyed this video, please consider subscribing our channel Ask, and please share this with your friends, and please press this bell icon for notifications so that you can get the new updates about this Rheology video series and other video series. Thank you, and thanks for watching, and hopefully see you in the next video.